Last week, we talked about how the magnetic field can create a force on a moving charged particle. I mentioned that you can create a magnetic field by having a moving charged particle. While this is true, the magnetic field it creates varies with time, which introduces additional difficulties. So this week, we are going to focus on the magnetic field created by a current, which is a bunch of moving charged particles, but it can be described in a relatively steady manner. Recall the formula we use for calculating the electric field is Coulomb's law. And one form of Coulomb's law says that the electric field is equal to 1 over 4 pi epsilon naught. Remember, epsilon naught was the permittivity of free space, and this whole term 1 over 4 pi epsilon naught was the Coulomb's constant, times the charge over r squared, and it's in the r hat direction. We could also write the Coulomb's law in a differential form if we have a charge that was spread out. In that case, it was dE equals 1 over 4 pi epsilon naught times dq r hat over r squared. And sometimes it would be more useful to write it in terms of r vector over r cubed. If r vector, it was easier to write than r hat. Now, there's no point charge equivalent for magnetic field, and that's because current does not exist in a point. Current must flow along a line. So we are required to use the differential form. Second, for electric field, we have this constant right here, this epsilon naught, which again stands for the permittivity of free space. For magnetic field, the relevant quantity is this term mu naught, which stands for the permeability of free space. Mu naught has a value equal to 4 pi times 10 to the negative 7th Tesla meters per ampere. So put this all together, you get what's called the Biot-Savart law. dB is equal to mu naught over 4 pi times I dl cross r hat over r squared. Or, if you would prefer to use the r vector form, mu naught over 4 pi I dl cross r vector over r cubed. So mu naught is the permeability of free space, I is the current, dl is the small differential piece of wire, similar to the dl from the force on the wire of last week, and r is the vector going from that particular point on the wire to the point in space that we are finding the magnetic field of. You also may recognize this cross product. You can use the same rules as cross product before. dl is the first term, so that your thumb goes in the direction of the wire. R is the second term, so your fingers go in the direction of R. And the result, B, is in the direction your palm pushes. This is a little less intuitive than for the force case, so there is an alternate right-hand rule that you can use for creating magnetic fields, is that you put your thumb in the direction of L, which is the direction the current is flowing through the wire, and your fingers will naturally curl in the same direction the magnetic field curls. So here is a picture demonstrating that. Thumb goes in the direction of the current, and your fingers will curl around in the same direction the magnetic field goes around the wire. Now, applying the Biot-Savart law is by necessity doing an integral, since this is dB. It can be a somewhat nasty integral, which I will attempt to do right here. So let's assume that this bit of wire is infinitely long. We want to find the magnetic field that is a point R from that wire. Now, like with the electric field, if we want to use this differential form and integrate, we need to find a coordinate that all of our terms can be related to. Same thing here. In this image, the coordinate is s. So as you move along the wire, dl is equivalent to ds. We can also use the Pythagorean theorem to say that the r magnitude is equal to s squared plus r squared square rooted, and that the r vector is negative s in this direction and big R in this direction. Now here is one place where things get a little easy. This term right here, dl cross r hat, or rather dl cross r. dl is in this direction, r is in this direction right here, and remember we can find the magnitude of a cross product by saying it is equal to the two vectors, or the magnitude of the two vectors times the sine of the angle between them. In this case, this is the r vector, this is the ds vector, so this right here is the angle between them. So dl times r times the sine of theta. But consider, the sine of theta times r is the hypotenuse, the sine of theta times r is this big R right here, which does make some things a little easier. We can say that dl cross r is equal to, in our new terms, r ds. dl cross r also has directions, so let's try this. dl, put our thumb in the direction of dl, fingers out in the direction of r. In this example, you would probably need to widen your fingers more than they can, but the result is that the magnetic field goes into the page at this point. Using the substitution, r is equal to the square root of r squared plus s squared, we get this, where ds is our only variable. And we can do this integral. This integral might be a little difficult, but I can tell you right now, it evaluates to 1 over 2, or 2 over r squared, which means that all of this put together, all of these constant terms times 2 over r squared, the magnetic field near an infinite wire is equal to mu sub naught I over 2 pi r. For clarification, I am not going to ask you to do this integral. You can get away with, in part, memorizing this result. The magnetic field near an infinitely long wire is equal to mu sub naught I over 2 pi r, where r is the perpendicular distance from the wire. Now, another shape of wire that we will see is of a circular section. In a circular section, the wire is curved around a point. We can again find the magnetic field resulting from this at the center point, where it's easy. Anywhere else, we would have to use a bit of trigonometry. But at the center point, we can rely on a few things. First is that the magnetic field, or the current, is always, and the wire are always perpendicular, or are always tangential to this point, which means that dl cross r is just dl times r. We can use as our coordinate an angle theta, and so in that coordinate, dl is equal to r d theta. Additionally, r becomes constant. In fact, nothing here changes. The only thing that changes is our variable d theta. So the magnetic field is equal to mu sub naught I over 4 pi r times the integral of d theta. The integral of any dx is equal to the range of that variable. So the magnetic field produced by a circular section of wire is equal to mu sub naught I over 4 pi r times, and I'm using a big theta here, where big theta represents the total angle of the wire. For a full loop, if the wire were a full circle, theta would be 2 pi, which means B would be mu sub naught I over 2r. In this example right here, if this is a right angle, theta would be 90 degrees, but that always needs to be in radians, so theta is pi over 2 radians. Also keep in mind that you can have multiple loops. If a wire wraps in multiple loops, theta can be bigger than 2 pi. Now, consider that the Biot-Savart law is a differential equation, which means when we apply it, we are adding up a bunch of small pieces of magnetic field. This means that we can have combinations of wires and loops, and we add them together through the principle of superposition. That is, we break the problem up into pieces that are easily recognizable, find the magnetic field from each of those pieces individually, and then add them together. We could also go in the opposite direction. Since we know that the magnetic field from an infinitely long wire is mu sub naught I over 2 pi r, we can calculate the magnetic field from what's called a half-infinite wire by dividing this in half, mu sub naught I over 4 pi r.